Hello, I am CCP Veritas. This is the talk Gridlock Talks Performance. It's going to be the rest of the team mostly, but I'm going to start us off. So in the context of Team Gridlock, when we're talking performance, we're usually talking server performance. I just kind of want to set us off as where I think we are, and then we'll talk about where we're going. And so how are we doing on server performance? I'd say we're doing pretty well. Not great, not terrible, we're doing okay. I have some numbers to back that up. We have 2,100 players in Jeddah, the primary market hub of EVE Online, which is a heck of a lot of players to have in one solar system. Now, usually most of them are docked up, and we saw recently, last weekend, what happens when they're not. Thank you for that. Yes, the ducks. But that's a pretty high number. I'd be hard-pressed to find another MMO that has that many players in their market hub. Any case, 1,000 player fleet fights are going pretty well these days. They're, again, not fantastic, but they're pretty reasonably good. And 3,000 player fleet fights, which we've seen a couple of, work. They don't work terribly well, but they work, and we're very happy about that. We hope you are too. So naturally, doing pretty well is not where we want to be. We want to be doing well or great. And I want to talk a bit about how what's in front of us to get there. The easy gains in server performance are long gone. When Gridlock was formed, 3 years ago? This is what we were doing. We were putting the performance analysis tools to work. We were finding very easy gains and deploying them very rapidly. We were able to get some very large gains very early, and it was very encouraging. Those days are done. Like, what we're left with is kind of the foundational hard stuff. And thankfully, we're working on one of those big projects right now. To introduce who that we is, I've got a few slides. And first of all, we've got our good friend CCP PrismX. You may have known him from his previous work as a database expert and also on the EVE API. And he looks absolutely fantastic in a dress. I'm not giving you a picture of that, but trust me. Second member I'm introducing today is CCP Mervangian. I don't know how you pronounce that. It's Mervangian or something. He worked on some skunkwork projects. You probably don't know about them, but if you do, they're pretty cool. And as his shirt shows you, he knows what he's doing. So we leave him alone mostly. The other team member we have, and to be clear, I picked these pictures. It's all my fault. CCP Hedgehog. He's fantastically well known for not being known. And I'm here to tell you he's absolutely fascinated with SpongeBob SquarePants. So if you also are a fan of Pineapples Under the Sea, he's your man to talk to. And it wouldn't be Team Gridlock without CCP Habakkuk. He's a wicked good QA member and is the only consistent member of Team Gridlock. Over the past 3 years, we've seen a lot of team members come in and out of it. He's the only guy who's been in every single incarnation. So to pass it on to the team, first of all, is going to be CCP PrismX, talking about how we load balance the EVE Online cluster.
Guys hear me? Yes, you can. Okay, so I'm going to talk a bit about a dev blog that I made, I think 6 months ago, and it's about how we balance the EVE cluster. Now, before I do that, I'm just going to mention the basic building blocks of the EVE cluster, and it's made out of 50-ish or so services. Some of them are just background services you don't know about, but just to take an example of something that you might know about, when you do corporation work, you talk to a corporation service. When you do market stuff, you talk to a market service. When you're in a solar system and you're shooting somebody in the face, you're using the solar system service. There's a character service when you do character stuff. They're all quite simple. Now, to break them further down, then every service which handles a very well specified area of work also is broken down into many different addresses. And addresses are, to make an example, like the market service, it has address 1,000,002, I think this is 10,000,002, and 10,000,003. These are what we call region IDs in EVE. So whenever you're dealing with a market of a certain region, you address the market service of that region ID. Similarly for the systems, the top one there is the JITA service. It runs JITA. The one below that I think is a MAR. I don't remember what the third one is, but they're all addressed on a solar system ID. So if you want to talk to a solar system, you request the solar system service of that solar system ID. Now, character services, they're kind of weird because we don't have a simple service for every single character ID. That would be crazy. So instead, we do a modulus calculation of the character's character ID with a n, which you just have n many character services. And then you know what service to talk to if you want to talk to get information about Kripa. Then you take Kripa's character ID, modulus n, and then you know what to talk to. Now, just to summarize that up quickly, we have a bit more than 16,000. It should be not 1,600, it should be 16,000. Sorry about that. So we have 16,000 different addresses, and we all estimate the peak hour value of these addresses every downtime. But we only have 248 nodes in the entire cluster, and they're all configured differently. Many of them only run solar system services, others run only market regions, some run many different services, and they're also configurable to only run a certain subset of those addresses within the service. So that's how we split all of Empire space away from nullsec and all wormhole space away from both Empire space and nullsec, and we keep GDA always on the same node alone. So when the service starts up, it has to anticipate, it has to somehow configure itself to survive that run. If it just throws out all the load to a single hardware, it'll not survive. So how do we do that? Well, we follow the kissing principle. KISS is a computer science term, which means keep it simple, stupid. And that's pretty much what we do. Now, if you imagine these explosions up there are addresses, and they have a load value on them. So if you say this is a market addresses, then the 32 there is probably the forge because GDA is there. And we basically just go through this, what we call a greedy least loaded node assignment basis. So we take the heaviest address and put it on the least loaded node, and we continue down that ladder over and over again. If that were to happen here, then we take the 32, put it into a least loaded node, the 16 goes to the next empty one, and the 15 to the next one. Now, if you followed me, then the 12, you'll understand that that goes to the 15. Now that becomes the second most loaded node, so the next one goes to the middle one. And we go on like this, slowly. Everything happens, goes to the lowest granularity of load, and then we end up with this. So this is the total sum load of these nodes. And as you can see, they are quite similar. This is good. Now, solar systems do not like kissing. What solar systems do is they like to group together in the same constellation group as they belong to. So if we just color these things up like let's pretend these are systems, and the color code says what constellation they're in. We do the same thing over again. The 32 goes there. As we know, the 16 goes over there. This all makes sense. 15 doesn't get to go over there. It's pulled over to that heavy node there because it's the same constellation. Now the algorithm continues like that. And you might think it's like innocent enough because it seems like it's going to be doing the same thing. But then this starts happening. And like, nope, you just don't get to go there. You have to follow your constellation. And that ends up like this. And now we have two nodes that are almost twice the load value of another one. And this is bad. So this is how it ended up in the summer of 2013. This was the old load balancer we had for solar systems. And, well, this looks weird. Because these are not constellation colors anymore. These are the nodes. Now we have two systems in the black rice region. This is just the black rice region. I gave it 8 nodes to balance between them. These two are probably not going to be very loaded. And if you look up at the CPU estimation up there, you can see it's almost 5.5 times, like the difference between the minimum and the maximum is huge. And the deviation, like this number doesn't really tell you anything, but it's we want to have this low. So we had to do something. And we just decided to like keep it simple, stupid. Let's see what happens if we make solar systems KISS. And that was horrible, because we ended up with DoDixie on the same node as a low-sec staging system, and nobody liked that. So we developed this new method, and to succinctly state that, iteratively sections down the entire set of systems in a node count many equalish balanced sets of neighboring systems. I've been practicing this sentence all week. So, just to show you what that means, because nobody understood what I just said. Basically what we do is we have 8 nodes. We take the entire region, which we just pretend it's the entire universe in this example, and we just throw it onto one node. That's all the blue stuff. Then we use some fuzzy, fancy math to calculate the boundaries of the region, as well as just making a wild guess in the middle and saying, if we split this in the middle, we'll end up with a 50-50 load. That is, of course, nonsense, and we can't expect that to actually hold. But what we then do is we measure the load on both sides of the split line, and we use a similar idea as binary search uses, if you know what that is, and we move the boundary down there, and we split again in the middle. Now we measure it again, and this is even worse, but that's fine, because we're going to do it again, and we're going to measure again, and now we're going to move the boundaries up again, and you can see what we're doing. We're just trying to zoom in onto this good split there. We do this iteratively for quite some time, and then we just pick the best solution, and we say, okay, split it like this. So we assign this half to one node and keep the other half on the old node. Now, we rinse and repeat this again over and over, take the larger part of this and split it again in a similar way. We end up like this. This is confusing, but this is 3D space on a 2D plane, and the split line is coming from behind and out through the wall. Just bear with me. Do it again. 4th step, get this nice teal color. 5th step, I don't know what to call this color. Versions of purple, I guess, the 6th one, the 7th one, and the last one, proper purple. Now, this ends up in a much better spread. I mean, yeah, the least loaded node is now more loaded, but we want hardware to actually use its hardware. We don't want to just sitting idly around. Now, just for comparison, this. See, standard deviation went down to almost a quarter of what it was. And if you look at those two systems there that had the dedicated node, they're not dedicated here. They're clearly not as heavy as this load balancer thought they would be. So just to wrap this all up, what did we gain? Well, as I told you, the standard deviation did kind of go down to a quarter of what it was. And that means there's a lot less of hardware waste going on. And every optimization we do gains from that fact. If you optimize a node that's running on 2% CPU, you're not optimizing anything. If you optimize a node code that's running on a 180% loaded CPU, you're still going to have an overloaded node. Better yet, the code is no longer in a T-SQL procedure code. That's why me, a database programmer, is standing up here explaining to you how we load balance our cluster, because I got into that because it was all in the database. Also, server starts up a couple of minutes quicker, and I'm quite proud of that. But now I'm going to hand it over to CCP V somewhere in that name, and he's going to talk about more details of this. So the clicker is over there.
Hi. Okay, it's on. Feel like Britney Spears. This is awesome. Okay, so I'm going to talk about, I'm CCP Merovingian. I'm going to talk a little bit about our excellent adventures in profiling in Team Gridlock. Okay, so what's telemetry? I'm pretty sure a few of you here have heard of telemetry before, but just in case you haven't, I'm going to just do a little run through of that. It's a performance visualizer made by Rad Games tools. It has some similarities to tools like Valgrind or Xcode instruments, which some of you may have used here. But I mean, what does it actually do? So again, just for people who aren't familiar with it, I'm going to give you some information on how we use it. When we've got a set of code that we want to see how efficiently it's running, how much time loops are taking to execute, how long it's taking to do things, we mark up code that we're interested in. And then we get back a dump from that sample of the code running, and we visualize it so that we can actually see where the hotspots in the code are. Typically, these kind of profiling tools are used for high-speed game loops, like Twitch games, like shoot-'em-ups and things like that on console games and PCs. So it's not perfectly suited to the way things run on the server side of things on Eve, and that's what Gridlock is mainly focusing on. So we have to do a little bit of work to get the data we need. I mean, typically, a Twitch game will have the same things going on once it's running in the main game loop. And it'll do the same things over and over again. Whereas on the Eve server, we have things that happen over multiple frames, and we have things that happen in a single frame that are very different from the next frame. So we have to do a bit of jiggery-pokery to get the data we need. Luckily, the guys at Rad Games are super helpful. So when we have feature requests or we need things fixed in telemetry or extra things that we need to work with the server, they're really quick to respond to that and help us out. So what does a telemetry capture look like? Just to give you an idea of how this stuff works, here's one from Rad Games' own site. And this is a good telemetry capture. I'm going to come back to why I said that in a minute. The main thing we're interested in here is this blue part, which gives us our call stack, how long this is the main loop at the top, and then how long different functions are taking to execute as we work our way down through the code path. And it's nicely marked up. We can see how long it's taking in here. As a bonus at the bottom here, we've got things like which thing is running on which core. So here we can see that this stuff here is running on the second core down, the blue thing. And that's pretty much what a good one should look like. So why have we only started using telemetry now? Well, those of you that have been around a while know that we've actually been using telemetry for quite a while. CCP Veritas has actually done a dev video and a dev blog, I think, where he was actually sampling live off TQ and getting data and things. So we've been using it for that. But day-to-day in CCP, we typically use it for client profiling, profiling the Dust 514 client, profiling the Eve client. We also do like a little bit of server sampling, and you've probably seen some of these server samples on devlogs. The one thing that really scares us, though, is sampling on TQ, because it's not been terribly stable, and we don't really want this to happen to you guys while you're playing online. So we've sort of held off on that a little bit. But it became increasingly obvious to us in Gridlock as we reformed that the work we're doing, we really needed this tool to work on TQ and for us to be able to see what's going on when you guys really play EVE. So one of the first things that we did was we had a look at the issues. One of the issues was literally just zipping up the data and processing it after a sample. That would actually cause some degradation in performance on the nodes. So we split that off onto a separate thread. That was fairly simple. And then we had a few issues where it would occasionally crash. That's not good. So we made sure that was a little bit more robust. Well, pretty much 100% robust now. Famous last words. We also had a little bit of a mini summit a couple of weeks ago when some of the guys from Shanghai, CCP Shanghai, came over. And we talked to them about what we've been doing, and they talked about what they were doing. And they're kind of looking at doing some similar things with battle server profiling on Dust 514. So we started thinking maybe we should sort of share information between teams and offices. So to that end, we formed a little, can't see that very well up there, but we formed what we call PerfCop, or the CCP Performance Community of Practice. That's not to say that we're going around snooping on other teams' code and saying, hey, this is really crap, you should make this faster, or anything like that, because that would be rude, and we'd be very unpopular. What it's more about is kind of sharing information, and sharing how we use the tools, and also sort of banding together and sending requests to Rad Games so they can do stuff for us. Okay, so more specifically, what are we using telemetry for in Gridlock? Well, I've already said that telemetry is pretty widely used in CCP anyway for client profiling. We also do a certain amount of development server profiling when we work in our own teams. And we've done more recently some more sampling of mass tests on CC. So when we organize those tests, there are certain things we're looking for, information we're looking to get from people playing EVE on CC. We also increasingly are reacting to unusual events on TQ. So if we see like a big fleet fight, or we see a specific issue that we want to investigate, or a particular node that's hot, we can jump on. I mean, and some of us have been jumping on from home. We get an email from the ops mailing list saying this node is hot or that node is hot. We can jump on, grab that data. If we feel like it, we can have a look at it at home. If not, we can go in the office and talk about it and try and figure out what these problems are. The other thing that we're doing, and CCP Hedgehog's going to talk a little bit about this in a moment, is building a historical reference data source of performance. God, how did I come up with that sentence? It's terrible. Anyway, it's basically saving data from previous samples, getting samples over different times and over different releases and different patches, and keeping that data, and trying to aggregate that data over time. And more specifically to what we're doing right now, because we're heavily involved in the Dogma rewrite, and ultimately we're hoping to push out Brain in a Box, we're going to be analyzing the impact of our work. We have some idea of what we think is going to happen, but as we've seen in the past, what we think is going to happen in a development environment and what actually happens when running this on TQ can be slightly different. So hopefully we can see the impact of our work, we can see problems, we can react to them, and hopefully overall we're going to see that things get better. Okay, so I've got a little bit of an example of what telemetry's actually done for us recently. And it's kind of a real-world example, which is pretty cool. So I was just going to share it with you today. So we deployed Rubicon a while back, and immediately after we deployed Rubicon, we noticed a marked degradation in performance. And if the thing you want to look at on this graph here is the red line that's going along. It's actually the CPU use per user. And this bit at the end just here, you can see there's a fairly large jump up. When that line goes up, that means that performance has gone down, it's making your life more difficult. So we kind of had CCP Explorer and CTB Veritas. If CCP Seagull was there, she was on maternity leave at the time, I think, but if she was there, she'd probably have come around to us as well and said, can you guys have a look? What's going on? So we did. So what did we actually do next? The first thing we did was locate a high-load node on TQ. Then we jumped on, took some samples of it while players were playing, which was pretty exciting. I mean, we tested this stuff before. We'd done some tests on CC, we'd done some tests locally, but we hadn't actually done this on TQ before in anger, so to speak. And that seemed to go pretty well. It was exciting in the office when we did it. Nothing went bang. we kind of hoped for that, but we weren't 100% sure. So we took some more samples. Then we had a look at what those samples gave us. Wasn't quite what we were expecting. So you remember earlier I said that what a good sample looks like. I said I was going to come back to that. This is our sample. This is a good sample. Okay, so looking at this right now, and this is with a little bit of benefit of hindsight, there's things here I can see that are wrong. There is actually, if I just go over here, this is sort of our server frame going from 13 to 14. And you can see some stuff at the beginning and the end here. There's a little bit here. That's kind of what we're looking for. There's some information in there we can use. But more worrying, there's just this repeated stuff going on. And there's lots of dark spaces in between. And what that tells me is we don't know what's going on there. So that wasn't terribly useful. But we thought, you know, we've got this data. We might as well use it. We'll see what we can find from it. So we zoomed in a bit. Yeah, great. Some more dark spaces. Just sort of emphasizes that a little bit. Then a little bit further. And we finally started getting a little bit of information out. And there's something there that we could work with. It didn't make a lot of sense to me, to be honest. I was fairly new to this part of the code. There's a lot of code in Eve. You might have heard that. But luckily, CCP Habakkuk, he had a brainwave. He's pretty awesome like that. And he recognized something. And he recognized this bit of information here, gave him an idea of what was going on. And it gave us clues to a couple of possible culprits. I'm just wondering if anyone here has a guess what it might be. That's one idea. Anyone else? Possibly, possibly. Another good guess. OK. So if you're right, there's CCP games/jobs, always looking for people. OK, so we had our theory. Some of those theories are good. And what we did was we went and we marked up those likely candidates in code. This is the thing. I mean, code gets marked up when we're developing it, and we test things on local servers, and we test things on development servers. We don't necessarily, because we haven't had this tool, we haven't been marking up this code that's going into production. And it's not running with markup in it. And this particular piece of code didn't have enough markup for us to pick out what we needed. So we went in there, and we just literally picked our best guesses, marked those up, and we deployed that to TQ in the next downtime. So we were able to react to this pretty quick. And then we took more samples. I'm just going to go back and show you what we had before. So this is the first sample we got. And once we'd marked that code up and sampled it again, we got something which looks a little bit more like the first slide I showed you. Not as many bright colors, but there's a lot more information there and a lot less dark space in between. So going back to the clue, this is the clue in the original sample. Not much information there. This is the clue when we've zoomed in to the second sample after we've marked it up a bit more. And there's a lot more information there. You've got tooltips and things, so you can hover over this and you can see the flow of the code and understand where it is and what it's doing. So what was it, anyway? See if any of you got the guess right. Turns out that it was the autolooters, which were newly introduced in Rubicon. So close. /jobs. OK, so at this point, this wasn't actually code that we'd worked on in Gridlock, so it was pretty much time for us to go to the bar. But recapping on what we'd achieved, we basically tested this code. We'd diagnosed a live issue on TQ, which was fun and exciting. And we found the cause, ultimately, of what it was, and we had an idea what the resolution was. We need to make this code go quicker. And we don't know how to do that, but the team that worked on it did. So we worked with them, we showed them the data we got, and they went away and they fixed it really super fast. It was actually very easy for them to fix. And we deployed a fix the next day, which went better than that. OK, so how much was the win? Now, this is a really difficult question to answer, and I was kind of in two minds about putting this slide in, because I don't know how this code works. I don't know what the problem was, really. I just know that there was a problem there. And the win is pretty big, so I'm not really going to comment on that. I think the code was doing a bit more looping than it needed to do, but this is part of the point of testing stuff on a live server. This worked fine when we were testing it, worked fine on test servers and things like that, but when it actually got into your guys' hands, I don't know what you did with it. But anyway, no. But the one thing I can say, just looking at this, is generally the code flow here, and you get a feel for it when you're looking at these kind of samples. The code flow here feels better in the blue one at the top, which is the second sample. OK, so after that, where are we at now? Well, we have a facility now that's stable. We always had telemetry before, and we could use it before, but we didn't really feel safe with it, and we didn't want to degrade the performance you guys had when you were playing. So we now have that. We can live diagnose performance issues more quickly and diagnose them. And we had some similar problems on Serenity, Eve China. The gameplay there's a little different, so sometimes we pick up different things. So for this, they had a couple of issues. We backported the code. They were able to sample it, and they found their issues. We kicked it backwards and forwards in the CCP performance community of practice. We're able to discuss this. I think they've fixed one of those issues, and there's ongoing work on other issues, which is all good news. And as I said, we've battle-tested live profiling, so it's something that we're going to try and use more in future. So where are we going with this? Well, as I said, we didn't know we had this tool before. It wasn't generally something that people knew they could do. We could jump on TQ and sample stuff. So we're now talking to people about new features, proactively marking it up in development so that we can actually see how it works when it goes out in the wild. So it's our job in Gridlock to spread the word about this, and we're trying to do that. And more specifically for us, with the Dogma rewrite and Brain in a Box, as I mentioned a little bit earlier, we're going to be able to take samples of the status of things now, the status of things when we put out some of these fixes. We can react to any problems with them, and we can work from a firm performance baseline that we have right now, and then develop further on that. And CCP Hedgehog's going to come on in a moment, have a little bit of a chat about how we're going to do that, and hopefully that'll enable us to see the impact of future deployments and make Eve better for all of us. Thanks very much. I'm going to hand over to CCP Hedgehog now.
Oh, yeah, thanks. Hello. Can I just start by checking that I'm audible? Yeah? Okay, that's good. I must apologize in advance. I've got a bit of a sore throat today. I will try to muddle through. It might hamper my intelligibility. I'm also Scottish, which will definitely hamper my intelligibility. But we'll see what we can do. All right, so you've just heard a bit about telemetry. And the short version of that is telemetry is great. It's a nice tool. We've enjoyed using it, and it's been helpful in giving us a handle on the situation. The visualizer, which you saw some screen captures of earlier, is nice. It's good for giving you a high-level overview of the situation and for giving you kind of context. So it's good for getting your bearings when you're investigating a problem, as was demonstrated in Murder's example. This button isn't reliable. Or my finger's not reliable. There's something not reliable here. There we go. So yeah, the visualizer is good for giving you context, and it's quite pretty as well. Here's an example of a real capture that we took on TQ, one of the sort of cleaner ones. And you can sort of see the breakdown of work there as Destiny, which is doing the physics simulation, figures out what to do and how to do it. But exploring these sort of traces in detail is quite difficult, actually. If you've got something like this, which is a sort of uglier one with a lot of kind of weird spikes in it that you might want to investigate, the problem is with a visual tool, your only your only option there is you just have to kind of manually zoom in, pick one of them that you're interested in, zoom in, just like in the movies, enhance, there we go. And eventually you get to some suitable level of detail, which is fun. And you can spend a couple of hours doing this, and it's very amusing. But it is actually time-consuming. And the problem is you've only looked at one spike. So having done this, technically, you have to kind of zoom out and look at the others. I mean, you might assume that they're the same, but they might not be. You don't actually have a way of knowing. So it's quite sort of labor-intensive. So if you had access to the raw data instead, that would be helpful. Because raw data is great. If you've got access to the data, you've got full control and sort of full awareness of the situation. You can see everything that's going on, anything that you're interested in, you can just drill into it. And of particular relevance to this part of the talk, it creates the possibility of doing your own analysis on the data. As luck would have it, telemetry in its new form, version 2, supports this because it's got the data is actually stored in a SQLite database, not their own sort of private data format, as was the case before. But if you actually go and look at that data and you load it up in a SQL viewer, it looks a bit like this. which of course is completely unintelligible. And there are about 70,000 lines of it on a typical capture. It doesn't help that there aren't even names in this, because the names are encoded as numbers for efficiency reasons. So you get lots of data. You almost get too much data. It sort of turns the data up to 11. But we have SQL, and SQL's great. Well, yeah, that's debatable, but for the purposes of this talk, we're going to pretend that it's great. So that will allow you to write custom SQL queries to let you make sense of this big sea of data that you've got. So as an example of that, you could do something like this, where you take the data we saw before and pull out the difference between the end times and the start times and add it up for all the zones. The zones are telemetry's name for a sort of measured piece of code, like a function or a group of functions. Add them all up, join it against the table that decodes the names, so you get something like this. So now we're starting to get somewhere. We can actually read what these things are. There are a couple of the usual suspects in there. Destiny, way up at the top, we've got handle message, and you've got the aggregate times, so you can kind of make sense of roughly what's going on. So that's quite good. But that's actually only part of what you want, because that kind of view is a top-level overview, a kind of aggregate of where all the time is spent. So it's good for letting you see the big hitters, the main functions in the system, but it's not actually that good at pointing at areas where there's room for efficiency improvements. Because the thing is, we already know that handle message takes a lot of time, because that's what the server spends almost all of its time doing. It's its job, it's to handle messages. What you really want to know is, well, which messages and which parts of them are actually causing the real load. We're interested in where the fat might be. That's the part that we can do something about. So one way of doing that is to measure how long things take, excluding the time that's spent on their children. And that gives you a different measure that's sometimes more useful from a performance perspective. So here's an example of that. We take another trace of handle message. So there's handle message being called at least 3 times, possibly more. And you can see those little chains of activity underneath the 3 main calls. And indeed, they're actually all different. It's doing different things, and the breakdown is different in each case. What really matters is the kind of heavy parts of the child tasks underneath all that. Because if you look at handle message itself, the amount of time just spent in that is not really that large. So this is why we want to be able to exclude child times to give us a more effective way of looking at the problem. It's a little bit tricky to do it. What you have to do is, for every zone, you've got to look for every other zone that overlaps with the original zone and is exactly 1 level deeper in the hierarchy and is running on the same thread. And then you have to add up all those parts and subtract them from the other total. But that's what you have to do. The way that's implemented, roughly, this is a sort of simplified version of it, but you do a bit of this, which is to pull out the data that we care about and scale it and so on. And then the real meat of it is in this part here, where it's finding all the overlapping zones with the constraints that I mentioned, and then joining it against a bunch of other things to decode names and make everything add up and do all the magic. So it's as easy as that. Every time you want to know, you just type all that in. User friendliness is great, and typing all that in isn't. So of course, you write a tool to do all this for you. And if you pipe the results of that out to a viewer, that gives you the option of kind of sorting that data, massaging it in various other ways, sort of after the fact. Because custom visualizers are, if not great, I wouldn't want to be immodest, but they are quite good. And here's one that we did. So it's the same data as before, piped to this custom viewer, and you can sort of see that the names are there. There's a bit more detail as to what's really going on, but the basics are the same. And you can see it's the same suspects. You have handle message up at the top, but that's because this is still sorted the same way. This is sorted by the time including the children. That's the inclusive time, the second column that you can see. But having got it in this form and having computed the exclusive time, which is the time without the children, you can, at the click of a button, sort by that, and then you get this, which is an interestingly different perspective. So a couple of things that we didn't see before kind of bubble up to the top, and the perspective is sort of changed. One thing to say about this is, as was sort of indicated at the start, there aren't really any kind of big wins, any easy things waiting to be done. It's not like there's some function that's taking 30% of the time or something, and by just fixing that, we can get a big improvement. It's not as good as that. I've scaled these numbers so that the one in the top row, the one that starts with 7.6, that's 7.6% of the total load. The one below it, 6%, and so on. So, these things, they're not negligible, but they're not huge either. However, they do give us an interesting view on things, and it turns out if you take just these 17 areas that we've got marked up here, the top ones, in aggregate, the total of them is actually slightly over 51% of the total load. So just by kind of focusing on these things and trying to see if there are any opportunities to get these being tighter, we do have the potential of making some real improvements. But even this is really just the beginning. There's probably more we can do with this kind of data. For the start, that was just the data from one small capture that you saw there. But really, it would be nice if we could aggregate this across different captures, because the profile changes a bit. It changes depending on whether it's a big fight or not, and actually the dynamics of the individual fight, and it even changes over time within a fight. So if we aggregate it, it might give us a better overall picture. We could maybe use some better visualizations as well. I have experimented with these. The textual form is, just the facts, ma'am, and it's kind of effective for some things, but maybe some graphs would be nice at some point. But it's a work in progress. This is just something we've been doing recently, and sort of describing it here for the first time. But this is already proved somewhat useful. It's already pointed us to some areas of interest. Just that flip of seeing the exclusive time lets you get some insights that otherwise would have been scattered in the visualizer in a way that you couldn't really pick up. And indeed, if you were looking at the names that came to the top of the list when we flipped the sort, you'll notice that one word tends to keep popping up quite frequently, and that word is Dogma, which is what we're going to be talking about next. Cool. Yeah.
Hello again. Yay, it works. All right, cool. So a lot of you in the audience might be wondering about this Dogma and Brain in the Box thing that everybody keeps bringing up. And I want to talk a bit today about how that's going and where that project's at. So Brain in a Box is a concept I introduced at Fanfest 2012. In short, basically, this is taking these skill books that are in your brain and pre-computing them. And I'll show some slides later as to why, at scale, that's a very important thing. But in general, your brain has a lot of things in it, and they do a lot of stuff, and wouldn't it be in need of some other node worried about that? I started working on that the following summer, and some things happened. Some technical, some personal. I got this promotion to technical director, and that kind of makes me not code anymore. Stuff like that. But, things. Some hurdles, so to say. So Dogma itself was found lacking. I want to talk about the technical reason that Brain in the Box has been so long in the making. The key thing that was missing in Dogma, and to bridge you in, the Dogma is the attribute system of EVE Online. If there's a number that goes to an item, you're talking about Dogma. Hit points on a ship, shield attributes, the number of skill points in the book that's in your brain, all of these are managed by Dogma, and their relationship between each other is managed by Dogma. Dogma did not have the ability to deal with a literal number. I couldn't say, multiply this by 2, because it didn't know the concept of 2. 2 would have had to have been an attribute on an item for Dogma to be able to handle that. And absolutely could have hacked this in. We could have had a brain item and understood that, like, negative attribute IDs were the literal positive numbers. So I could say, like, the brain's attribute -20 is the number 20. Like, that could have worked. But no, like, that's too far. And this is so basic of an ability that really the Dogma system should be able to handle it. So what we've been up to is rewriting that core of Dogma, that core of attributes and modifiers, not only to be able to handle literals, but to be more flexible in the ways that game design wants to work with it, and as well as our game programmers. So this is a very simple picture of how Dogma works today. There's an attribute on an item, and it does some math to an attribute on another item. This is how it looks in practice. This is the drone interfacing skill points attribute in the red outline there. It has a modifier down to the skill level, computed to be 5 because I'm baller and have a lot of skill points. That then computes out to the damage multiplier bonus on, again, the skill book in your brain, and the mining amount bonus, because it gives bonuses to both things, also still within the skill book in the brain. There's, once again, some more modifiers that take those bonuses and apply them either to your drones or to your character, because that's how mining drones get their bonus. They harvest them from the character. It's a little dirty, but it makes sense, right? Yeah, okay. So if we look at this damage multiplier down here on the Hobgoblin 2, you can see it's receiving a bonus of 100% from the drone interfacing skill book. Because again, level 5, I got skills. But the actual numbers there, 1.7 or 1.92 and 5.28 don't make a whole lot of sense, right? That's not a 100% bonus. It's because there's other skill books that affect that attribute. If we turn this view on its head and look at all the things that can affect that single attribute, the picture looks like this. So here we have 3 skill books, all giving a bonus to damage multiplier, all being evaluated separately, all being managed separately. This is why Brain in a Box is necessary, because there's no reason that the location node, the node that's handling the simulation of your spaceship, needs to care about what bonuses there are. This should all boil down to a single number, which is then multiplied by 1.92. So that's ultimately why we're working on Brain in a Box and why we need literals. So again, this is the current picture, and this is what we want to be able to do. And there's a bridge step needed to make that happen. And it looks like this. If you separate the attribute from its item and have the relationship be from the attribute to the attribute instead of from the item attribute pair to the item attribute pair, all of a sudden you can have attributes that don't have items, and they can happen to have the value 25. And nobody's the wiser. So that is the rewrite in a nutshell. It basically looked at the core of Dogma and said, Dogma is a graph in the computer science sense, right? There's nodes and there's edges. It's a graph. We know how to deal with graphs. Nodes are attributes, so those are the actual numbers. And on the edges, we have a mathematical operation. They multiply, they add, they divide. Pretty simple stuff, right? So the current system, if you look at it conceptually under the graph way, it's storing those edges in large global dictionaries, which makes finding what modifies you very expensive. I know who I am. I'm attribute 5 on this item. I now have to go to, I believe it's 5 different setups to try to find all the things that can modify me. Similarly, if you want to add a different kind of modifier, you now need to add another one of these lookup tables and look into it every single time you want to compute something. So this isn't something we've done in a long time. We haven't had a new type of modifier, I believe, since drones were introduced to the game. It's been a while, and it's something we want to do. So when we took those lookup tables away, a lot of features relied on them to be able to query what bonuses were in place. The most prolific one was gang bonuses. When you have a booster in your fleet and someone who receives that booster, it sets up the bonus directly from either the leadership skill book in their head or the module on their ship to the receiving pilot's ship. And so when that person leaves the fleet or leaves the system or turns off their module, that system relied on those global lookup tables to find what bonuses it had given and then revoke them. Now, the programmers in the crowd are probably now understanding why that system is so fragile. But the good news is, in the process of this rewrite, we've rewritten that system entirely from scratch, how those bonuses propagate. And it makes a heck of a lot more sense to us and should be a lot easier for not only mortals, but also computers to understand. So yeah, they need to be re-implemented. In short, we took that hurdle, and that's the best PowerPoint animation I've ever made in my life. So currently, the rewrite is in kind of a QAing phase. We have it in a sandbox off of our main development branch. And the fantastic CCP Habakkuk is a very busy man breaking the hell out of it. As it becomes harder and harder for him to do so, we'll be starting looking at putting it on public test servers. And once we're all through that, we'll be putting it out live. Once that's out, then we start working on Brain in a Box and other related projects. Are there any questions? Do we have time for questions? I think we do. In simple terms, what does it mean to the average player? Which part? The rewrite? Okay, so the Dogma rewrite in layman, to the average player, it doesn't mean a whole heck of a lot. The rewrite itself has about the same performance profile as the code previous, but it allows us to do more. Once we get Brain in a Box in, we expect that the load of jumping, docking, undocking, having your ship blown up, basically all ship changes, voluntary or otherwise, the load of those is going to be much lower. This is the predominant load in JITA. So once that's in, the JITA cap is going to be much higher. Anybody who's part of a 100+ player fleet that's trying to move between systems, that's going to be much smoother, things like that. Yay! I believe we have just a couple more minutes. Yes, we do. Anybody else? Will it improve session change timers? I don't believe so, but that's open for discussion. That's a bit of an unrelated thing. How the session changes propagate across the cluster is something pretty different from Dogma. But we might tweak them anyway, just for funsies. Yeah. I'm sorry, I didn't catch the first part. Will you be able to load grid when you jump into head GP? Probably. No guarantees. I mean, it's a vibrant place. What's this next secret project I'm working on? Wouldn't be much of a secret now, would it? Okay, fine, I'll tell you. So Brain in a Box is a good idea. It brings a lot of the load off the location node. But one of the main reasons that I wanted to do this as a clean rewrite instead of just getting in the impact of literals is having attributes as their own thing puts in a very clean abstraction layer between that and the rest of the gameplay that uses them. And that level of abstraction will allow us to take that core of attributes and modifiers and bring them into another language. Possibly C. Yeah, you know how big that is. That's the next super secret project. Yeah. The question is, any chance of these changes being deployed in the summer expansion? No. No, this is beyond summer expansion. I mean, the state of the sandbox right now is that most things work, but for some reason right now, jumping between solar systems is completely broken. You might want to do that in EVE Online. So we've got some work to do. So let me set the expectation bar here. I'm hoping these changes are out before the end of the year, and ideally with Brain in a Box as part of that. That's my hopes and dreams. That's not a commitment, just so we know. I think I have time for one more. Yeah. Optimal range for the drones? Okay, so the question is, oftentimes with drones, the value you see in the client in like the show info is incorrect depending on the state of the drone. That's right. Brain in a Box is not going to help with that. However, the simplicity of the new Dogma should make it easier to fix problems like that. That particular problem is because the client doesn't always have perfect information from the server. And hopefully, if we sit down and really dig into why drones don't have that, we should be able to provide that to the client. So no, but there's hope. Okay. And that's going to do it for us today. Thank you very much.